Welcome to Exam 1 review session. It's always nerve-wracking because you don't know what the professor's going to ask. You haven't taken an exam from him. So this things to worry. Well, let's alleviate some of that. But I also can't stop myself from being a teacher all the time. So I got to teach you how to take an exam, how to prepare for an exam. Maybe you already know. Maybe you're great at it. But I got to tell you, first thing, make a list. A list of the topics that you have to cover. Sometimes I'll even make a really long list. That's like kind of procrastinating the actual exam preparation, but sometimes that list is a good thing. I'll like make a list of all the homework problems that were assigned, or maybe even all the examples, or I'll try to make connections between the homework and the examples, see what kind of topics could possibly be asked. And so here's my rough list of the topics that we have covered in Chapter 11. We have the book available to us. I even brought mine. Use this in conjunction with the notes, with the examples that were done in class, the videos that, for examples that we didn't get done in class, if you happen to be in my class, and you have that. By the way, if you're a member of the club, we should make it a club. We should get like hats of the recitation club. If you're on the Blackboard there, all my notes are on there as well. So you have the videos too, the links to the videos. And Mrs. Deal is sending me a text, but that's not important right now. She's still important to me. In case you're listening, Laura, she wouldn't listen to this. So anyway, you want to look through the book and see those examples too, and try to organize your brain. But don't spend a lot of time doing that, because mostly what we want to do is practice solving problems. So we have fundamental kinematics. That was one of the first class. That's we could write those fundamental kinematics equations down. Also, by the way, I should have brought like copies of the equation sheet. If you're a professor, if you're my student, or I think Dr. Orlob's student, and I'm not sure Dr. Sahai what he's doing, but whatever he's doing, there is an equation sheet available that I will be using, and that will be attached to the exam. So definitely, when you're practicing solving problems, have that equation sheet in front of you. All these relevant equations are in the upper left-hand corner. So you don't have to look at the whole sheet, just the upper left-hand corner. It's sparse. It doesn't have every kind of equation that you could possibly need in there, but it's got a good amount. So we have the fundamental kinematic equations. Some projectile motion. I think it was actually kind of class 3 where we did that. Constant acceleration, I believe that's in the second class. Relative motion, that's in the second and third classes. Constrained dependent motion, that was in the second class, I believe, right? And these are pulley problems, right? So, pulley problems, right? Constrained dependent motion. Rectangular coordinates was class 3. Class 4 is where I introduced coordinate transformations with the path coordinates. And then once again, class 5, we had the path coordinates, right? So there's a lot of words right there. But trying to organize your brain. So one of the very first things in solving any problem is problem identification. What kind of problem is this? And then you start reading the words and start getting the clues. And there is the section of the equation sheet that has the relative. Actually, this rank, I don't know. I think I keep forgetting this every single time. This is not on here. The second law is not on this exam. So that needs to be smaller. All right, so I have a bunch of different problems. Okay, so here is a really too long problem. I did this one year as an example. I'm just gonna throw some problems out and talk about them. Maybe not too long, but this is like a relative motion problem that's combined with a constant acceleration problem. I think this one is too long, but I did do it. It is in a video running across here. Here's a bunch of projectile motion problems that I have put on there with variations of projectile motion problems. I could guarantee you, at least on my exam, there will be one projectile motion problem, and there are a bunch of different varieties that can be done of them. Some of them are just slight variations, but enough that could be kind of challenging. I will not be asking a problem like this where you have to find the angle. It's too hard to do, so I won't do that. But then on my Blackboard and also on the Blackboard for the recitation. I've also put a bunch of stuff that I had, actual problems from the Coast Guard Academy, where I asked, and I just put them up there, gave them away. The S16 means spring of 2016, so if you want to know what the code of those are. So some of these I wrote, some of them are taken from, some I adapted from the book. I kind of want to leave these up to you and not cover them during this session, and maybe if I pick other types of problems so that you can simulate the exam yourself. I will also, reinforce this idea that I am not going to ask these problems on the exam. I will ask something similar, sometimes very similar, sometimes quite different. Sometimes there'll be multiple aspects to them. Like you might have, this might be path coordinates with relative motion combined together, that type of thing. All right. So I'm taking requests. What kind of problems would you like to do? Any particular problem? And we can just do our best. I'll do my best to make it clear.
Can we do a problem with path coordinates?
Path coordinates and polar coordinates? I think I have
Path or polar.
path or polar. How about path and polar?
Sure.
Okay. So I have a guy. I don't know if I asked this a couple years ago. So I'm going to ruin it, but here you go. All right, so here's my problem. I have this dude, so this is his spring 2021, so I'm burning this one, I guess, but only for this year. Maybe then people just have to go hunting for it on the videos right here, where we have this camera, right, and these guys are going to go around this hoop-de-hoop, right? So here's a problem that would puzzle people because they didn't get an identical problem to it, and they'll say this is an unfair problem. I'm telling you now, it's a challenging problem. But let's read it carefully. That's probably one of the most important things on the exam, right? Is what is being asked? That first step. How do I get that? By the way, a lot of times that's where people lose a lot of time. Sit there and stare at the problem, hoping for divine intervention to come down. And I'm all about the aha motion, the aha moment. We wanted that aha moment, but that aha moment isn't going to come down from the from up from the heavens. It's going to come from inside here, and the only way you can really get to it is start moving, start getting something, start writing. I know this information is already written down on this problem. Start writing down what you know. The active motion, the things that you. By the way, you now have something written on the page. Gotta tell you, very, very easy. That just stared at the problem and never really got started because it's nice and blank, all white and clean. And if I was in my own self-interest, I wouldn't get on my knees, as I've done in my class, and say, please don't leave a problem blank. But if actually there's a kind of an upside for me, it's like real easy to grade. Like real easy. Like I'll give some partial credit. That as long as it's partial credit that shows some amount of knowledge of how to solve a problem. But anyway, so as we're going through, I would proceed to write stuff down that I knew. And hopefully the act of doing that was going to trigger what we know. Well, let's read this. 2 U-Heart students are riding a roller coaster and approach a loop-de-loop. With the radius of our loop right here, I might have written that down somewhere. Our loop equals, and I think a lot of times what I'll do is I'll write this thing out and I'll make it like a little box with with the values in it. Just so you know, that's very typical of me. Because then I can make multiple versions of the exam so that people don't cheat during the exam. Because I think people cheat a lot of times as an opportunity. So if I prevent the opportunity, then they won't be tempted to cheat. So I'm actually doing you a favor. So there'll be multiple versions of the exam. I've had people, when I wasn't looking, slide an exam over to the person next to them. And cheater's going to cheat. When they cheat, a lot of them, they just go all in. Like, that person puts an ampersand in there, I'm putting an ampersand there. That person draws a smiley face, I'm drawing a smiley face too. But anyway, they'll write down the numbers of the neighbor's thing, and they'll write thing I don't like. So just knowing ahead of time, just don't do that. But anyway, write down what this is, what the loop is, on a straight section between right here. So there's a straight guy going right here. All right, so I'm trying to understand this side of the communication. So this guy's moving a certain number of feet. I decided, looks like I made that 50 feet. In a straight line, when at point A, they're going at this speed, that right there tells me this is going to be like a constant acceleration problem. Right? I can see, I can just go ahead, jump ahead and go, that's a constant acceleration. He just told me this distance and this initial velocity. I know we have a constant acceleration problem. And when they reach the top of the loop at B, all the way up here, their speed is VB. Okay, so they had a speed here, and now they have a speed here, and this is a distance right there. Are they about to tell us at a having slowed at a constant rate? Okay, so constant deceleration is what we read into that. There is a camera, because they want to like take your picture and then charge you as you go out the door at the souvenir shop at the exit of the ride, and they're really going to try to stop you from taking the picture of that picture. They hate that, but you'll do it anyway. What the hell? Why not? Because they already got your money. Why are they going to give more money? There's the camera and follows their movement. When they are at the top, the camera has this distance, that right there, and is at that angle right here. So we're already kind of getting the idea. This is path coordinates. Did you recognize this path coordinates going on? Right? Right here, that's the tangential, and there's the normal. We also see that there's polar coordinates going on here because we got a camera, we got a distance and an angle. And that camera is like following them. What they're asking for, the rate of the camera, we're going to find the rate of the camera, theta dot, radians per second, at this instant, and the perceived acceleration of the camera, students coming towards it, right? So that's going to be the R double dot, that thing right there. Must use a coordinate transformation as part of this problem. So we all understand what we had to do. So let's try this one. We'll call this the S21 exam 1, problem 1. Okay. So my R loop was 35 feet. That's what I decided. My XAO, that was that first initial distance right here, was 50 feet. And my VA was 35 feet per second. My VB was equal to 20 feet per second. And my RB with respect to C, 25 feet. And my theta is equal to 35 degrees. So when this thing is like right here, it's going to come up. I'll make it look like that right there. We know this VA right here, and we know this VB right there. So we have a distance. We could find what this distance is going to be from here all the way up to there. I might want to call this delta S from A to B. That's going to be my 50 feet plus the arc, half of a circle that's going to go right there. So you could just say, well, that's going to the angular distance that the 180 degrees is the same as pi, right? And you could just multiply that angular displacement in radians by the radius. So that's going to be pi times this radius right here. So that radius we said was 25 feet. What did it say? 35? No, it was 35 feet right here. So we could find that it's going to be 159.95. I think you can go 160 probably at that point, right? Doesn't hurt you. Now we want to know what the deceleration is going to be, because we know they're going from 35 feet per second to 20 feet per second, excuse me. What do we use? A constant acceleration that relates velocity and position, right? This guy. And I'll go delta S here. Is that everybody okay with that? So we just plug the numbers in. 20 is what's the final one. The initial one is going to be 35. We're looking for what the acceleration is going to be, and this is 160.0. We can go ahead and round that to that. So what we'll find, this should be a negative number, right? We're decelerating, and sure enough, it is 2.579 feet per second squared. We also, okay, so if let's call this is going to be the tangential acceleration, right? That's the one it's going to be facing in that direction, though, we should note. Because the tangent is actually that way, but we have negative, so it's actually that way. And if we were going to write this, we also need to have the normal acceleration too. Remember that that's going to be AN is equal to V squared over rho. That we're talking about here is going to be the 20, because that's what's happening at that position. And the radius was still 35. That's going to be 11.43 feet per second squared. So, going to make sense that we, as a spot in here, we're going to write this out and as the value, as the vector. It's going to be ET plus 11.43 EN. I hope you don't feel shortchanged if I gave you one of the rulers that doesn't have the protractor inside it. I can't find these in bulk, and they're very fragile. I mean, you could just bend. I'm not going to demonstrate, but it'll break just by, and I'm not going to try it. I'm not going to show you. There's not much, and just break. It's like, but it's a cool little thing, right? It's very, very useful. Anyway, sorry. So we're going to do the coordinate transformation. And so our coordinates, let's see, I'm going to put the camera up here. We'll draw it on top. Here's the camera who is looking at them. Beep, 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 beep. And here's a horizontal. Boop, 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 boop. I like making noises. More noise is what we need. More noises. And of course, this distance right here, this R, was the RA. I think it says A. A with respect to C, yeah. It should be B with respect to C. Is it B with respect to C? It is B with respect to C. You lunkhead. Don't talk to me bad about yourself. Just be nice sometimes. So that's actually going to be, if we were to look, I'll draw it parallel right here. Here's going to be our polar coordinate unit vectors, ER and E theta, little hat caret on top. Here's going to be our EN, and then right next to this velocity should be ET, phone home. That's a dated reference. So we will write those in here, superimpose them. Is there any other kind of impose? Superimpose? I don't think I need to start going down. Oops. Less talking, more thinking. Said every student I've ever had. And I had a student here that took my classes with me, 5 separate classes. I know what you're feeling. What the hell? It must have been required classes, right? Oh, the last one was an elective. I was like, dude, seriously. You should reconsider. All right, so that's our normal and tangential, and then we're going to superimpose. Now, one thing I would mention: be careful of the 45 degrees. Avoid 45 degrees. So we know that it's 35 degrees, but let's make it look even smaller than that. I like to extend the lines too, right there. Okay, so here is going to be our ER. Perpendicular. Here's going to be our E theta. Right there. So we have E theta. Boom. And our angle that we're going to use, this is the angle right there. Boom. And because we made it non-45, it's obvious where the other ones are, but also because we've practiced a little bit. And then we make a coordinate transformation array. Now, I'm not sure if Dr. Sahai is doing this or not. We don't communicate enough. We should communicate more. So I can explain here I won't go too quickly in this. I'm not sure he's asking for these. This was it was a couple years ago. Dr. Orlip and I and Dr. Rico, we kind of got together and said, hey, this coordinate transformation gets done in this book they used to use with the unfortunate name of Tong, Benson Tong. His last name is Tong. Weird name. But anyway, he did that in this book, and they don't cover it here. So we're like, let's keep using that because it's such a nice way to approach systematically getting coordinates aligned with each other. I tend to pick the one that I'm starting with on the top row, but it doesn't matter. It doesn't have to be that way. And then but you want to, what's really important is that you set the thing up and then you use it systematically. All right, so here is the difficult part of this, the challenging part. And now this is a challenging one. This is not one that's like, many of them are repetitious. They have the same, they're the same arrangement. This one has a weird arrangement because they're upside down and backwards. But it is all the same thing. So you just have to take a moment and systematically approach it. All right, so let's start with ET and compare it to ER. Okay, because now first we can see they're in opposite kind of directions. Right here, that one's going to that way, ER is going that way, so you expect to have a negative value. You can also see that if you were to lay this on top of the extension of R, it would be adjacent. So we know that that's got to be a negative cosine of theta. Might as well go from left to right, go to the EN, take a look down at here. And when it comes to the ER, you can see that ER is going this way. If we were to break this EN into components aligned with this, we would have like, I'm going to draw it real lightly. That would be the component, and that would be a component, right? Breaking the components. So it looks to me that the one that's aligned with ER is in the opposite direction, and it's opposite from the angle. So it's a negative sign. Does anybody have any questions on that, what I just did? It makes sense when you see it. You need to practice it yourself, right? You can't learn this thing passively by watching somebody else do it. You have to organize your brain and get it like all straightened out. And then practice it a couple times so you do it with speed. If you do this quickly, you'll have more time to do something else on the exam. This is just a pure muscle memory kind of thing almost once you get it down pat, I think. But maybe I would there are brief moments where you want to just take a little bit of a pause and go, I got to concentrate on this. And then the rest of it is a little bit faster. E theta, we're going to look at that compared to E tangent. No, I'm sorry, E tangent to E theta. Maybe that's the way I was looking at it. Here's my tangent, and here's my theta. And looking at that, they seem to be kind of in the same direction. And by the way, we've already established this, so you're expecting sine of theta because they always have that pattern where they're diagonal from each other. Once you have that established, this looks like it's going to be a sine, and basically the only thing we have to do is it positive or is it negative? They look like they're in the same direction. In fact, if you were to break down the tangent into components, like here, I'm just drawing that real light, you would see, that's in the positive E theta direction. So that's got to be a positive sine theta. And then lastly, here, we can just jump to the conclusion this is negative cosine, right? Because we have the diagonals, and either one of them's negative or three of them are negative, right? No other way that it could happen. So we know that should be negative cosine, but let's double check it. We have the En down here, and we could say that the E theta, yep, sure enough, E theta is in that direction, but the component that aligns with the En is down that way right there, and it's adjacent, so it's a negative cosine. I maybe went over that longer than I needed to, but I want to make sure that anybody who's not familiar with it has some passing familiarity with the thing. All right. Next step is we want to take, for next step, and I didn't write this down, but maybe I'll write it down now, that the velocity of this guy is going to be equal to 20, and let's call it ET. This is one of those, duh kind of things, right? It's obvious. You know why? Velocity is always tangent to the path. I mean, it's almost like the velocity actually kind of defines where the tangential coordinates are, right? So this is just speed times the natural unit vector that you would have, right? That unit vector gets defined by the velocity. But what we do now is we pass it through this column right here, because it's all tangent. So what we're going to find is we're going to have this equal to 20 times negative cosine of the angle, which is 35 degrees. And that's ER plus 20 times, and it's going to be positive, sine of 35 degrees, and that should be E theta. So when we do the math and get this out, we'll get a negative 16.38 ER plus an 11.47 E theta. These are still feet per second. So when it comes to polar coordinates, we've just found, and I use these words often to describe our mission when it comes to polar coordinates, we're looking for the variables of interest. I think I read it somewhere. I don't think I came up with it, but I don't know if our book refers to what the variables of interest are, which, the VOI, as I call it, is R dot, R double dot, theta, theta dot, theta double dot. And when you're doing a polar coordinates problem, it's good to think of it in those terms. Here's my mission. Try to find these. Sometimes they're given to us, but maybe they're like kind of mixed in with the words. So you have to identify what they are, and then you plug them back into your equations. Or the other way around. So this is the other way around type of problem where you know the motion, and now you're trying to find these variables of interest. So we found the first one is going to be R dot is equal to negative 16.38. I don't need that ER. Why am I putting it in there? Sorry. This is just the component. This is just the part of the component. The variable of interest is the variable. Feet per second. Now this one over here, this guy is, we could call him V theta as a component, is 11.47, and that's equal to R theta dot. Therefore, we can find theta dot by dividing that 11.47 by the radius, And that's going to be the 35 feet. That's going to be the R loop. So 35 feet. And I have that being as point. So this is actually the first question, part A, asked for this. Yay, we're almost there. The challenging part is to find that R double dot. And there's a homework like this too, by the way. I think there's on homework 5. There, in my class, at least problem 3, I think has the same kind of idea. Not identical to this, but similar. Now we need to do the transformation of the acceleration. So that's going to be a little bit longer here. We started out, let's see, I got to get this back on the screen. Maybe I got to lift it up a little bit. So look, sometimes it's like juggling. So I could do an in-between step, but I feel so comfortable with my coordinate transformations, I could jump to this step. Sometimes, but if you want to be more systematic, you'll do this in-between step and then go to the next step. But here I'm going to collect all of the like terms, collect the ERs together and the E thetas together. So I start out with my ET, and I go to this guy. So I have negative 2.579, and that's going to be negative cosine of 35 degrees. And now I'm going to go and take this one and multiply it by the sine of theta, the negative sine of theta. So I'll put my minus right there, 11.43, and then I'm going to have the sine of 35. ER. ER? Yes, ER. Okay, so, truth be told, because the nature of the question only asks for R double dot, you don't actually have to do this next step for this problem. I will do it, but you don't have to. If you're trying to save time, have any amount of fear, maybe you want to leave some gap right in here. There are no instructions that told us that we had to get the whole thing. They only asked for R double dot. Maybe we want to leave this little space right there, get the R double dot, and go to another problem. And then if you have time at the end, you just for completeness, right? And for some people, I know that's really tough to do. A lot of people just really, and that's a good thing, actually. But in terms of test-taking strategy, time's your enemy. So let's try to economize where we can. We wouldn't necessarily have to do the next part. And you might even write a note next to that. I don't know how much, if that would take you a lot of time. But let's just you want to communicate with the professor. Let's say, hey, I know how to do this, but I'm saving some time, but I don't know. Just a suggestion. So anyway, we go through the next part of it. And so we're going to go through, this one, and now we're going to go down, we're going to go through this row right here. So we're going to take this, which is the ET, times that. So we got a negative 2.579, and we're going to multiply it by the sine of 35. I didn't need that parentheses, but I put it there, so I'm going to keep it in. And then lastly, we want this term times this. I'll put the negative right in there. So 11.43 times the cosine of 35. Boom. And we have E theta. And we just work the thing out. And I have to go to a new page because I didn't economize my paper, but they'll make more paper. And if you feel bad about wasting paper, you should plant a tree. It's nice planting a tree, except when they die. Very difficult to keep a tree alive if you just forgot that you planted a tree. But it's really neat when they take off and they do live in your yard. Oh, the joys of home ownership. I planted a lot because I didn't want to see my neighbors. Neighborly guy. Okay, so this turns out to be negative 4.443. plus negative 10.84. I think Lori should actually listen to some of my things there, spiels, because I'm really just entertaining her, and she's not here to appreciate it. She laughs at everything I say. I'm hilarious, as far as she cares. It's a good situation. I recommend it. All right, so we want to take this and now get the, okay, so the only part that we really need was this. And what we want to do is find that R double dot. So that this guy right here is AR, and then you could call him this guy A theta. And so AR is equal to R double dot minus R theta dot squared. And then if we cared about the other one, A theta was equal to R theta double dot plus 2 times R dot times theta dot. Seems like, wow, that's confusing. That's a lot of stuff. But if you start remembering what the physical significance of each of the parts are, it really kind of helps to put it into context. And it's not that much difficult. It doesn't. And if you start doing that with every single equation that you see in every single class, you start learning the language of the thing, and it doesn't seem nearly as daunting as with all the alphabet soup that you have thrown out in front of you. It's my helpful suggestion and how I somehow survived to get to be the tenured associate professor you see before you. My best friend in high school just wrote me the other day and said, this just proves Jane Green was wrong. It'll never amount to anything. Except she said it with a southern accent. R is 35, right? That's what our R, yeah. Oh, wait, excuse me. What's that? I think you're right. It's 25. Thank you. I was looking at this R. Really, you got to get back on the swing of things. This guy is in terms of variables of interest, is the R, right, that we care about, because that's going to be the distance. Thank you so much. I'll get my head back on straight. I was thinking of Jane Green. It's her fault. I can tell you some Jane Green stories. She was angry. Okay, so the theta dot right here, that was something we had to get from the velocity right here. So this was a step we needed to do right here to get this theta. So we had 0.4589 squared, and now we're able to get R double dot, which ends up being, according to me, 0.8213 feet per second squared, which is interesting because it's coming at you in the negative R direction. It's traveling at the negative. So it's got, so if you notice up here, that makes sense. This R dot makes sense. It's negative, but it's a bit surprising that this is a positive value. I tell you, acceleration can really mess with you when you're trying to rationalize it, because that's not the direction it's moving. It's just telling you the change that's about to happen to R dot. So now R dot is probably going to become, less negative than it was before. Like it was a negative one because it's coming at you. That is the direction of motion. The rate is shrinking. It's getting smaller, but the rate at which it's getting smaller is decreasing. Therefore, it's positive. Very hard for acceleration, but necessary to think of it in those terms. Always trying to get does this make physical sense? Really important thing. So what are we doing with time? Oh, wow, 1:39 for one problem. And by the way, I time my problems. This was a 13-minute problem for me. I'd expect a student to do it in 26 minutes, right? I usually try that. So and I give the values of the problems equivalent, right? So I add them up together, and I usually try to make sure that I'm under 37.5 minutes for a 75-minute exam? Usually a little bit less than that, and then I will figure out, and I'll reduce some aspect of it. Like I probably asked for theta double dot in this originally and said, no, that takes too much time, so I reduced it.
Stupid question, sorry.
No,
When
no,
you go
no
back
stupid
to
question.
the diagram, what's the difference between AR and R double dot?
Okay. Oh, excellent question. AR and double dot. Okay, so let me go back to this main equation right here. I say this in my class. I think this is helpful to give you a little bit more connection to what the hell is going on here. There, I do a derivation of this, and it's in the book, but that's really just trying to digest where the hell did that come from. But if I want to make an argument, like to explain each of these terms, the easiest way to do, first off, is explain what the R double dot is. And I say, often we'll use, like if you were sitting on it and spinning, I use a fishing pole, right? And so the rope's getting longer. And if you happen to be like sitting right there and that thing could pivot along this right there, that is our R. And the R double dot, right? So this would be the length of the thing, R. And then if it was getting longer, that would be the R dot. And then if it was getting longer and longer and longer and longer, more quickly and more quickly, that would be R double dot. Right? But let's take, that's stationary. It's not rotating. Now let's do one where R doesn't change. But theta dot, we are moving. That describes a circle, right? So we have a circle. So another situation here, here's a circle. And here is R. And we are moving with an R, a theta dot, like right there. So we have a velocity right here, V. And what is that V? Well, you could find it by taking R times theta dot. Right? That's what you would call the rate, what we call the transverse, the theta direction. All right, but R is not changing. Okay, so if this thing is rotating and it's going around, I described this, so it's a little departure here. If I am on, right, so if I am about to get on an off-ramp right here, and I am driving in that direction, what is my velocity component in that direction? 0, right? I'm sorry. We're fine. All right, but now if I get on this exit, right? So, and I was saying I'm traveling in that same speed right there. What is my component in the downward direction? Something, right? We went from nothing to something. Therefore, we must be accelerating in that direction. And if you get them closer and closer, what you'll find is we have an acceleration that's going towards the center. We always have an acceleration going to the center. So we have, in this case right here, let's just say that we're going at a constant theta dot. We have an acceleration. It's going towards the center, which is going to be V squared, and I'll call it R. Well, here's our velocity. What would happen if we were to shove that back in there? We get R squared, theta dot squared over R. What is our terms? Boom, boom, R theta dot squared. So this is centrifugal acceleration in disguise. In the case of a circle. But we don't always have a circle. Sometimes the R changes. So we have this component. So that's why R double dot is not AR. AR is a combination of R double dot and centrifugal acceleration. I don't know if I needed to go all the way through that to explain, but I thought it would stick better to explain it that way.
Are you using the terms centrifugal?
Oh, dude, interchangeable because F those people. I don't remember what it's supposed to be. Whatever, man. One is an imaginary one, right? Is that there's imaginary, because, truth be told, there's another type of dynamics. There's lots of types of dynamics, and sometimes if we use D'Alembert's principles, which a lot of books did, I did, before, that's just run out of style, everything was centrifugal. Because we had this imaginary direction, even though, we would always the mysterious acceleration is the centrifugal. The centrifugal is the one where you're going around the curve and you feel like you're being thrown to the outside, but you're not actually being thrown to the outside. You're feeling the car pushing you towards the center. You're also experiencing if you did have a magic genie and the car suddenly, poof, disappeared, you'd keep on going straight. Momentum. You have linear momentum. You no longer go around the curve. So that car is saying, can't go straight. You got to go that way. And you just feel like you're going to the out. But in terms of, here it is right here, F equals ma. D'Alembert said F minus ma is equal to 0. All the accelerations suddenly turned backwards. But we were about to see, we don't like D'Alembert. Like Newton. So anyway, so I will I'll use the wrong words. Let's do another problem. Does anybody have any questions on that? Anything we did? Can you see the mindset that we need to go through to be able to puzzle through a problem? All right. Only way to get better at it, practice. Do another one. Put something, not the same, not identical one, something you've never seen before, put it in front of you. Challenge your brain. Challenge yourself. Lift heavier and heavier weights. Okay, so anybody got any pulley system? It's hard to find pulley systems. I could make one up. I don't know. Okay, so pulley systems, really, I would put them into two categories, broad categories maybe. I'd say you have ones with one cable and then one with multiple cables. Even harder to do, man. All right. So let's see. I'm going to try to tell you where I get these things from. But you could probably read what it said right there. Ooh, that's an interesting one. I'll tell you where I got it from. Okay. So, and a lot of times I will see students who don't make the marks onto the pulley, onto the drawing or whatever on an exam. Like, make sure you're marking up the thing. The thing? All right. Here's the system that we're dealing with. And it's not going to be glamour shots here. So we're going to come down. This is not too complicated, but if you don't know how to do the problem, it feels complicated. Oh. Sorry. No, don't. Get your head in the game. All right. That one. It's A. Here's one up here. Ah! Yeah, the coil is bending through space. All right. So this guy is starting off VA, or I guess maybe at this instant. A lot of times for me, I see this as an opportunity to double dip on a problem and to say, ooh, I could say that it's starting from some speed, moving with this acceleration, or telling you that there's a relative motion between these two. And basically, all these problems come down as number of equations and number of unknowns. And trying to keep them straight, what direction is. So what we're trying to find here is find the velocity of B relative to A, which is another way of saying B with respect to A. And then say B if acceleration of A is 0.5 feet per second squared downwards, delta YB at delta T equals 5 seconds. So it kind of has that too, as part of it. So first thing, let's start out with try to figure out our equations here. Let's see, so I didn't name, this is D, we'll call that D, and the rope right there is connected. This is, I guess I'll call it E, but I don't think I have to give it a name. He's C. And so we will measure it from right here, right there. And then also here. Well, I should do that. So I'll say that here to here, I like to go downwards, write the equations, and then all of a sudden reset my coordinate system so up is positive, because I think down positive just bothers me. But as long as you have as long as you're like consistent all the way through, and then boom, just that equation is freestanding, right? You can multiply it by -1 as soon as it's an equation. It doesn't really matter, as long as it's both sides that you do too. So this is going to be SB, and double checking that, I think, and then we're going to have SC. I don't have the solution to this, so I could totally screw this up, by the way. It's just the first thing I saw that was like, ooh, yeah, that's multiple cables. All right, so we'll start out with L1, and just because it's here. So let's see. The only one that we could really write down, so this is, by the way, we'll follow this cable. That cable goes right here to there, right? So this cable, but this is a separate cable right here to there. You can see that, recognize it? All right. It's one of the first steps. So for this equation, for L1, we only have one SB. And now we're going to go for this one. Distance should be, and I like to put parentheses around them. I really like parentheses. I over parentheses, all parentheses. It's like a hug. I give the numbers. It's a little hug. Put a little hug around it. I don't know, sorry. Anyway, weirdo. Okay. So this distance is going to be that minus SC. And then lastly, we're going to have this, which is going to be SA minus SC. That distance right here. And we don't have to, but let's see, we're going to have 2SB minus 2SC plus SA. We could wait to take the derivative of them, or we could just write the thing out. Equals 2VA, no, 2VB, just looking right at it. 2VC plus VA. And write his buddy too, the acceleration of the thing. As long as you write it correctly, staring right at it, write something different. Question my brain sometimes. All right, now we do the other length, the other rope. This length to me looks like it has to be SB. It's a little confusing because there's an SD written right there, but it's really the SB that's the real reference. We don't really give a shit about what happens to D. It's really SB is B is what we really care about. Yes, sir.
So why does SA go to the SB goes to the middle of the 40?
Because this distance between D and B never changes, so I can just ignore it. I guess sometimes we're even thinking about, like, when I write L, the length right here, I mean, I'm keeping the mindset of the length, but I'm also making all the constants I'm lumping them all together with on the left-hand side, because they're all just going to disappear anyway. It's a shortcut, I grant you. So L2 is going to be our SB plus, looks like SC to me, right? This distance right here. Don't see anything else. So it's just a short little cable that's going back and forth, back into there. So that's going to be VB plus VC, which is also means that VC is equal to negative VB. This is going to be interesting. What happens here? Man, I'm a little nervous now. Be bold. No, we're going to be okay. All right, sorry. I thought everything was going to cancel out. Whew. It doesn't. Just take the derivative here. Actually, you could just take the derivative of that one. Say AC, because we don't give a shit about AC, so we want to swear as much as possible. No, that doesn't make any sense what I just wrote. We want to get rid of things that we don't care about, and we want to see that. So what we'll do is we'll put that guy back into there, and that guy back into there. I could have numbered these and said to combine, but what will happen here is equals 0, I'll do it in 2 steps, VB minus 2 times minus VB plus VA, right? So therefore, you're going to get for VB plus VA, sorry, VA, right? AKA, we're trying to find we're trying to find this, right? So what we could do is say VB, we know what VA is going to be equal to. So we'll say that it's going to be equal to negative 1/4 VA. Therefore, VB is equal to negative 1/4 4, aka negative 1. Negative 1 feet per second. But the question asks for VB with respect to A, right? Which we know is VB minus VA. By the way, this means, because this is negative right here, I should have done the reset personally. I should have put this as a negative 4. If I was consistent with what I had said previously, that I said I like to do the coordinate reset. So let me be consistent. I'm going to say, okay, say coordinate reset, and boom, so that up is positive. And therefore, that VB is going up, right? Because this equation right up here, it said VB and VA are going in opposite directions. And the VA is 1/4 of what VB is going to be. So that's why I'm saying coordinate reset. I'm going to put a negative 4 in there. So I say that the answer means that that's going to be upwards. Something I point out, not that big of a deal, but never use a minus sign and an arrow next to each other. It's like saying it ain't no good, right, in English class, that you've used a double negative. So don't reverse the arrow by putting the negative in there. The arrow is enough. So don't put belt and suspenders in there. But this is important. By plugging this into here, we go B with respect to A is going to be, the B is going to be 1, whereas minus, it's going to be minus 4, right? So you're going to end up with 5 feet per second, if I did that correctly. And that answer is going to be upwards. That B will appear to be moving at 5 feet per second if you were on A. If you're taking a ride on bucket A or block A, and you're observing B, it would look like it's going up because you're going down. And then the last part of this was to find if the acceleration of A was 0.5 feet per second, we would want to find what the velocity, how much displaced of B, right? So what we could do for this, probably the easiest way to approach this part, right, written right here, is let's find out what the acceleration of B is going to be. We could probably get our head all turned around backwards because we were just asked about this relative motion, and you start going down that rabbit hole of relative motion, but the most straightforward thing is go, I can find, because I can take these two and add and combine them together, and I can find what the acceleration of acceleration of B is going to be, and then I just do everything around B. So let's see, that's going to be sorry. My attention span sometimes is about an hour. It always makes the fun part of the class right around the last 15 minutes. You just never know what's going to happen. It's exciting, though, right? That's Mr. Positivity injecting in the bright side of that sumbitch. Where did I go right here? Oh, I said that this is going to be negative AB, right? Am I doing this right? Someone who actually has an attention span left, please make sure I'm right. So I think I got that right. And we ended up having, it would make sense, 4 times acceleration of B plus the acceleration of A. So we would find that the acceleration of B is going to be negative 1/4 the acceleration of A. And they just said that that was going to be downwards. And we did our coordinate reset. Counts, still counts. I'm going off the corner of the page here. So negative 1/4, and it's going to be negative 0.5, because I said that it was going to be downwards acceleration. And so what ended, so that's going to is that going to make it 1/8? Is that right? Yeah, okay. Feet per second squared, and it's going to be going upwards. So we already found up above that this thing is moving 1 feet per second upwards, right? Initially, because we were told that VA was 4 feet per second, and that means that this is 1 feet per second going up. So if we want to have the delta Y of B, set it to be YB0, which we're going to say, well, shit, let's just make that the reference. Or they were going to ask for delta, which would mean that we would just subtract this from that over there, so that would be delta Y. Now, by the way, I wrote delta Y, so truth be told, that was not very even, we didn't even need to write that down, because it's inherent in the delta Y. So we go VB original times T plus 1/2 acceleration of B times time squared. So we'll have 1 times 5 seconds plus 1/2 times 0.125, right? That's this guy over here. And then 5 seconds squared. Portals could so 25 times that would remember. I wouldn't do that. Yeah. So 6 point. I could not do this in my head, and I don't feel bad about it. All right, there's 3 sig figs. Give 4 sig figs. I don't care about 4 sig figs are fine. 5 sig figs. That's just nuts. Because the truth is, if this was real world, we had all those things. Would you think that this was going to be exactly that much? If this thing was 6.7, I'd feel lucky. I use the analogy of the aircraft carrier, right? I can estimate how much the next aircraft carrier is going to cost. And you tell the admirals, it's going to be this many billion, this many million, this many hundreds of thousands, this many thousands, this many dollars and 58 cents. And then you go over to $7 billion. You seemed pretty certain what it was going to cost. But you didn't know. Hell, you didn't know. Don't imply certainty you don't have. By giving a bunch of sig figs just for the sake of putting a bunch of numbers down. All right, what kind of problem? Days. Tired of this shit. I'm tired of my voice. Gotcha. Want to hear about my new guitar? Mrs. Deal said, you know, this has been a gauntlet. You should reward yourself with a new guitar. You know how many guitars I have?
Too many.
Never would there ever be too many. I couldn't have too many. It's approaching 40. Somewhere in there. Depends what you consider a guitar, though. So walk it back a little bit. Mandolin? Okay, that's one less. All right. Violin? One less. How about ukuleles? I only have 4 of those. Bass guitars? That should be a guitar, right? But what about a stand-up bass? That's one less then. Okay. What about a banjo? What about a 6-string banjo tuned like a guitar? Just play it like a guitar. It just sounds like a banjo. Okay, banjo's no good. What about a guitar that's got a computer inside it that makes it sound like a banjo, if I want? Is that only a portion of a guitar? And I have 2 of those. Tell them because the technology is 10 years old. Mrs. Deal said, okay. And I said, well, I have one in mind. She said, no, now I'm scared. I said, you ought to be. No, I got to tell you how much it costs. She said, tell me how much it costs. And I'm like, I don't think we should. But anyway, there she is. Oh, I've always wanted a reissue of the 1958 Gibson Carina Flying V. Only 81 sold in 1958 because they were way too ahead of their time. Now they're worth somewhere in the $300,000, but I did not pay that. This is a reissue. But it's a cool guitar, iconic. I've always wanted one. So I own one now. I want to go home and play it. But let's keep doing some of this instead. That's what I'll reward myself by playing some late into the night. It's also no longer January. Dry January was a fun time. We're done with it though.
I have a question.
Please.
When we
A guitar related one?
I don't like guitars.
Okay, you should buy one. Start playing.
Now, if we were to solve a system of equations, for example, there was a homework that had 4 equations to solve.
Mhm.
Is it okay if we use matrices?
I personally would be like jumping up and down and excited that you used matrices to solve simultaneous equations. That would be like, I'd be the thrill of victory. But I don't know about other professors, because what's difficult is to communicate how you solve the thing. And, alarm bells, not your fault, but the people who came before you, alarm bells go off when people see that you magically get a number that I couldn't see. So it might take you longer to draw the matrix out and to demonstrate what you did than it would be worth it just to plug and chug and solve the thing around. I don't know. That's my advice. But you showed me that you could do the matrix thing, I'd be like, cool, beans, can you teach me? I used to. In fact, I know a whole lot of different special little matrix, but if you're talking like a 4x4 matrix and you could solve that thing, cool, man, cool.
What about 4x5?
No, I can't do 4x5. Oh, you mean, see, I always pull everything over to the left-hand side, so it's always symmetric. Anyway. Another type of problem. Want to see projectile motion problem? We haven't done a projectile motion problem. There's different categories of projectile motion problems. Let me find my list of them. Sometimes you know the initial velocity. Sometimes you're trying to find the initial velocity. So those are 2 big categories that you have. Sometimes because projectile motion, I jokingly say, but I believe to be true, but I don't have any documentation on this, But I believe it was, you could consider it the first dynamics problem, the first in the history of mankind. Because you wanted to throw a stone at some food and hit the food so you could not be hungry. There you go. It's a projectile motion problem. And then we, society built up and we suddenly didn't like the people over there. Figured out all kinds of ways to get that rock, throw it at those people. And actually, when when you were younger in the crib, you figured how to get your rattle and bean your kid sister in the head with it. Lego, I don't know, whatever, your projectile motion. So it's sort of an important problem, but they're still quite difficult. So let's take the classic skiing one. Have you ever seen, probably not, old man telling you about things that used to be on TV is an exciting thing to hear, I know. But there used to be this advertisement for ABC Sports. There's the thrill of victory and the agony of defeat. And when they showed the agony of defeat, this poor son of a bitch on a ski thing hits off the side of the ramp and starts going end over end, and then you're just like, you can't hear it, but you can kind of see here the bones breaking, right? The agony of defeat. So every single time when I see one of those things, the agony of defeat. And they actually did years later, they stopped running that thing a long time ago, but they do every now and then interview the agony of defeat guy. He's not an American, but the equivalent of, you guys leave me the hell alone. But let's see. We have the agony of defeat guy. And I would never go off of this thing. I would imagine that they're pretty darn intimidating to stand at the top of this thing. You got to have some guts. And I didn't do a good enough job of showing that there's a little ramp thing right there. Right? So we could draw the trajectory up here of this is at point A. So here is your or that is point A, and here's your V that's happening right there. But of course, gravity is going to win. Gravity wins. Some kind of like boom right there. You're going to land somewhere. We'll call that B. And here's a little dude in skis. Yay! I'm going to try to draw him. He's leaning forward. Here he goes poles out like that right there. These are the important things that make life fun. So anyway, let's see. This is like 4 meters to right there. And let's see. I didn't capture the theta A going right here. This in the same spot right down to here was 100 meters. And they did the fun thing that I try to avoid most of the time. But here you go. Here's your 3 and your 4. Instead of giving you an angle, they gave you that thing. I don't like doing that, but it's just me. What can I say? I got baggage. So what we're going to try, so find VA. Very, very common problem to find VA. The other problem is to get to know VA and to find this distance. I think we had a problem like that, the homework I assigned. So, but practicing these things, it's a bad time to remember during the exam. So you want to challenge yourself and organize your brain. Can I work through a problem like this? Remember the main thing, instead of trying to memorize any kind of equation, the main thing is remember that it links both the x and the y together. So that we have x as a position is going to be equal to v. I was going to say this the wrong way. XO, but I almost always make that someplace and treat it like it's 0, plus V, I guess I go OX. I never get those things right, times time. And then Y's position is Y0, and Y isn't always, like, so I'm going to decide that right there is 0. Y0 plus V O, Y, T, and then this projectile motion, so we can go ahead and replace the acceleration with gravity and make it negative. That's not written that way on your equation sheet. We just have the regular old, here's what a constant acceleration thing is, but you should remember this. And if you do forget that gravity is equal to 9.81 meters per second squared, or 32.2 feet per second squared, that'll be helpful for you. Still thinking about that flying V. All right. Here we go. Okay, so one thing to start with in this that can be helpful is to also write down that VOX is equal to VO times the cosine of, in this case, theta A, how they have it written. They call that theta A, VOY equal to VO sine theta A. As you're going along here, you might also establish what X and Y are going to be at the final point. So X, in terms of its final location, is going to be 100 meters times, trying to think my way through this right here. I think it's going to be 3/5. Is that right? No, it's 4/5, you son of a bitch. 4/5, right? Because this length is 5, right there for 3, 4, 5, and this ends up being 4/5 times 100. Should be 80. These meters. Got to remember to use meters for that. A lot of people make that mistake, like just go on one of these and whatever they had that focused on. Why? Recognize that if we're going to treat, depends, we say, they gave us 4 meters right here. So I am thinking that y0 should be 4 meters, but then y, when you're done, is going to be negative whatever that distance is going to be, right? So that should be 3/5 times, negative 3/5 times 100. Or, I got to look it up because I'm dumb. What is it? What was the y? What should it be? Don't make me take my calculator out. What's the 60, right? Negative 60? Yeah. Not a smart man. But I have a flying V. I made it this far. It's a fucking miracle. Jane Green, she was like, she's like, Tina Dale, you're about as dumb as a person I've ever met. You're hopeless. I love to torment her though, man. She's old. She's like really old. And one day she says, I was taking my mother to go vote the other day, and I went, your mother's still alive? My mother's still alive? That's right, I'm a dinosaur. Direct. Let's go back to this. I'm going to take this and say that time is going to be, I'm going to combine that with this. So this is a typical thing to do, where I'm going to say that time is going to be equal to x over VO times the cosine of theta A. So I have combined these two things to get that. And then I'll combine this right here and move that back into place. We'll get a y plus y0. No, not y plus y0. Frustrating. So I'm going to replace this with this VO sine of theta A, and replace this t with this t right here. So that's, I'm going to put the denominator over there, V0 cosine theta A, and then the x gets put right in there. So this is interesting. Those v's are going to cancel out. And if you wanted to, you could make that the tangent of theta A. Now, we already know those values because you just turn those into numbers if you wanted, but I was just going to keep them in this form right here so you could recognize that this happens. In terms of solving the problem, it might be quicker to just keep, make them into numbers. But to note that these two disappear right there, and then and they're going to go away. And we can also put the numbers in here if we wanted to for this. We're going to replace the t squared right here. Let me double check something there. Oh, let me mention a interesting strategy that sometimes happens. If we don't know x and y, a novel strategy is to not replace t with what we're about to do. This is a shortcut that you wouldn't predict, that you do replace this t, but you don't replace that t if you don't know what the values of these things are going to be. Wait a minute. Did I say that wrong? I think I said that wrong. I'm going to back off on that. I'm trying to think. There is a scenario where you find, you do that step, and then you can just find the t. You just find the time when the thing is going to land. But let's just go back to this. We will replace it. So we end up with, I think, x squared over VO squared cosine squared of theta A. People forget that square all the time. That cosine square right there. But the good news for this problem is we now know everything here except for VO. 25 degrees. I'm sorry, I did not. But you're absolutely right. It was written. It wasn't written on the diagram, so I didn't put it out there. It was written right there. Thank you for reminding me. Clear how you would go about the rest of it? Yeah. Now you just got to be careful with the calculator that you get, a little bit of math, but you got all the essence of it. But the core of any of those problems generally is that time is linking the x direction motion, which is a constant velocity problem, with the y direction motion, which is a constant acceleration problem. And as I mentioned, if you were instead trying to find the position, it's sometimes a little bit more challenging, not necessarily. You might need to do the quadratic equation. Right? So for one thing, you would know, for in this case right here, what you would do is you might want to write an equation for the slope. Right? And one strategy is to say that distance right there, you could say, you could instead, where we wrote this thing down right here, instead of 100, we put d in there, right, for our distance. And then, so when we plug this back into here, we have d everywhere, and we'd have a quadratic where we had to solve for d. And there's two possibilities numerically. A lot of times, one of them will make no sense at all. But if they do make sense, this is all about whatever the values are. This kind of thing that could be around. A lot of times, if you did have two that were close, you'd pick the one that was the shorter of the two distances. Unless it didn't make any freaking sense at all. It's just a numeric artifact. And sometimes that's true. Sometimes it'll be, it'll be a negative number. It's like, well, that doesn't make any sense. The same thing true. Sometimes you might want to find the time when it lands. Because of that, you might have a quadratic for time as well. Requests for next problem? Burned out. You're tired. You're nervous? Of course. You said no? Of course. I didn't say okay. Someone was using, throwing their voice and it was lying on you. Ventriloquism. My wife has, when she was maybe 8 or 9 years old, got her ventriloquist dummy. She wanted to be a ventriloquist. But then, she went through a period where she was, kind of scared of this ventriloquist doll. She saw, this movie with a ventriloquist doll. So she was just a little kid. And my brother-in-law, her sister's 13 years older than her. So anyway, used to hide this ventriloquist doll in the house in various places, and when she gets shocked. The ventriloquist doll even came to our wedding. It's in our possession somewhere, but she won't tell me where it is because I would put it. The point is that ventriloquy is, I don't know, there's no point to that story. It was a pointless story. It's now recorded, by the way. That is if the audio got recorded. I don't even know what the audio is set to, what microphone is set to be. Be all just a silent movie. To go back and overdub it, not worth it. Questions? I can keep talking. Want to hear more about my guitars? How about my amplifiers? Oh, I've got a lot of amplifiers. I got an amplifier problem. Tube amplifier. I built a couple. Actually, I built 3. They're not very reliable. Turns out, if you don't know what the hell you're doing, they make noise though. Well, you got the Bogner Ecstasy. Is right here. Right next to him is the Friedman. This is the J.J. Cantrell Jr., the J.J. Jr. Friedman amplifier. My full-size Bogner Ecstasy is right up in there. Oh, what's funny is I bought a Chinese a Flying V kit that I built. $50. And then I bought this one. I don't want to put them next to each other to see if they look good. And there's my Fuchs audio. It's supposed to be like a Dumble. Have you ever heard of Dumble amplifiers? Yeah. Howard Dumble is a recluse amplifier builder. You had to audition to get him to buy you an for him to build you an amplifier. Here's my Vox, my AC-15. Walter Woods. I will try.
Aerospace engineer.
Neat. Okay, he's right. Bunch of schmucks. It's fun though. Here's my Van Halen effects pedals. See, I have another. That's only one of my 3 boards of effects. I have that delay. It's not working well. Well, the delay is working, but you're supposed to triumph for the thing. Here's a. Okay, so this is. I'm not sure what the occasion was for getting some of the guitars out. They're my black Gibsons. There's my Van Halen guitars right here. Although there's 2 more in the back. Right there. Okay. So yeah, this has been exciting right here. Here's a collection of skulls. Disturbing. Here is, how big of a Van Halen fan am I? Oh no, you can't see it. No, I'm a liar now, I guess. Oh, there it is. Oh, there it is, right there. You see that? Right there? I had front row seats to the Van Halen concert with my wife. Eddie sat down on the edge of the stage, smoking a cigarette, and he handed me a cigarette. I kept it. So I have his DNA. I could clone Eddie. Oh, that might be more expensive than that Flying V. All right, what do you say we can't stop this video now?